let W be the set of all vectors of the form W defined by the 3 by 2 matrix C minus A minus 6B, and 2B plus A. And so we want to show that W is a subspace of R3, or find a counterexample. So to get us started here, let's rewrite W as a linear combination of its column vectors. So we have W is given to us as C minus A minus 6B, 2B plus A. And in order to rewrite this as a linear combination of its column vectors, we just need to reorder this. So we can think of this, our first column would be minus A. Column 2, there's no B, so we would put a 0 here. Then we have minus 6B, 2B. And then our third column is for C, and we only have a C in row 1. So that's C, 0, 0. And we can now rewrite this as a linear combination of A, B, and C. So I can think of this, really breaking this down. I have minus A in our first column, plus 0 minus 6B, 2B in the second column, plus our third column, C, 0, 0. And now we can rewrite this as A multiplied by the column vector negative 1, 1, 1, plus B multiplied by the column vector 0, negative 6, 2, plus C multiplied by the column vector 1, 0, 0. And so what I'm going to do here is I'll let this first column vector be V sub 1, our second column vector be V sub 2, and our third column vector be V sub 3. And so we conclude that, therefore, W is defined as A multiplied by vector V1 plus B multiplied by vector V sub 2 plus C multiplied by vector V sub 3, which is a linear combination. And let's give ourselves more room. So this is a linear combination of the vectors V sub 1, V sub 2, V sub 3. So then we can conclude, therefore, by our theorem, since vectors V sub 1, V sub 2, V sub 3, and R3, then the span of these vectors is a subspace of R3, which we just showed is the breakdown of W, is a subspace of R3. And that is our beautiful final answer. So since we were able to rewrite W as a linear combination of these three vectors that exist in R3, then we know by our theorem that the span of these vectors defined by W is a subspace of R3.